Everyone, I'm Eric Nielsen at New Mexico State University. I'll be chairing the first session, which is on stars. Before we get started, I just want to remind everyone to check out the code of conduct on the website about how to conduct yourself while you're here. I'll be keeping time for the speakers, so it's 12 minutes of talk and then 3 minutes of question. If everything works properly, my Zoom background will turn from green to yellow to red. So yellow means you have 2 minutes left, and red means you're eating into question time, and please stop so that people can have a chance to ask a question. And I'll become increasingly distracting as we get further and further into the red. So with that out of the way, I'll turn things over to Brett Morse from the University of Bern, who'll talk about the Olin Wilson Legacy Survey, or OWLS.
Thank you for that introduction. Can you see my screen okay? Okay, great. Thank you. So my name is Brett Morris. I am a postdoc at the University of Bern. I did my PhD at the University of Washington, which is how I became so enraptured with the 3.5 meter telescope. And I'm going to share with you some work that I've been doing with Suzanne Hawley and Leslie Hebb over the last somewhat more than a year now, which we're calling OWLS, the Olin Wilson Legacy Survey. Some motivation first. I'll explain what this is and why we're doing it in the next few slides. So the number of stars that we know host exoplanets continues to multiply. And I'm sure you've seen plots like this before from my colleagues. We love to flaunt how prolific the planet search community has been in recent years. And you can see that here, the discovery of transiting exoplanets, which are the green segments of the bars, is just exploding lately. And as we discover more and more planets orbiting nearby bright stars, we have great stellar astrophysics work to do because we've got stars to characterize and planets to characterize. And a mantra that has evolved from our field is that if you know thy star, you may know thy planet. And so we are endeavoring to know our stars as best we can. One of the things that we know that planet hosting stars do is that they are magnetically active. And when I say magnetically active, this is roughly what I mean. In the image on the left, this is an image of the sun, which is one of the only stars that we can spatially resolve with enough resolution to see that there are dark features on its surface. You can actually do this with your eyes if you use proper eye protection. Please don't stare at the sun. And these dark spots are regions of the photosphere that are cooled by magnetic activity. If you look in a broad optical bandpass like your eye does, you would see a dark spot. But if you look at the image on the right, which is taken in a narrow wavelength region near the calcium H, singly ionized calcium line, you can see that the region around the spots is brighter than the mean photosphere. And so if we focus on just this narrow wavelength region near the calcium H and K lines, we can measure emission from excess emission from the active regions on the star and get a disk integrated sense of how active the star is at a given time. This is really neat because magnetic activity affects observations of exoplanets, and I'm going to motivate this very, very briefly. My favorite star, the star that I spent most of my dissertation on, is called HAT P11. And this star is rather unique because it hosts a transiting exoplanet and it has a load of star spots on it. And during transit events of the host star by its close-in warm warm Neptune-sized planet, we see these we see with the Kepler Space Telescope, the image on the right, which is a light curve. And you can see that during the transit event, which is the typical U-shaped photometric feature as the planet passes in front of the star, there are these superimposed bumps that occur when the planet passes over dark regions on the stellar surface. And so we used this to trace the magnetically active regions on the surface of this star and resolve it with better resolution than we could without its transiting planet. And so one of the things that we did with the 3.5 meter telescope is that we continued to monitor the amount of calcium H and K emission coming from this star. we found that the S index, which is a measurement of how much calcium H and K emission a star gives out, varies like this, where the black points are archival observations from Keck, and the red points are observations from the 3.5 meter. And you can roughly trace out one cycle in an activity cycle here, where the activity index was increasing to about 0.6. And through the Kepler years, it remained at about 0.6. And then it dropped down and came back up in a kind of a V-shape depression in S index centered around the summer of 2016 when we were observing. And so we want to be able to make curves like this for many stars, including as many nearby bright planet hosting stars as possible, so that we can characterize whether or not their stellar activity is influencing the observations of their exoplanets that we are likely to take in the coming decade. It turns out that the shell spectrograph at APO is really an ideal instrument for this kind of task because of several reasons. One is the wavelength coverage of the shell covers calcium H and K beautifully. And so here I'm showing you 3 spectra of different stars that have varying levels of chromospheric activity. The tick marks on the x-axis are the H and K lines themselves, and they're highlighted in little red bands. And so you can see that 51 Peg, the first known transiting exoplanet of, sorry, not transiting, first known exoplanet orbiting a sun-like star, has very, very little chromospheric emission, whereas the star on the right has a whopping huge amount of chromospheric emission. And we can study how the amount of chromospheric emission varies with time in order to measure the activity cycle and study its intensity and its duration. We're doing this for a somewhat large sample of stars. They are mostly bright GKM stars with a few F stars sprinkled in there. They're mostly planet hosting stars, so their names often start with HAT or WASP or Kepler or K2 or TESS. They also draw from legacy S-index archives, including the archive that Olin Wilson himself assembled and that his collaborators continued into the 90s and beyond. And we have some good overlap of targets with historical spectroscopic surveys, including those from Mount Wilson, but also HARPS and Keck, which allows us to draw from the huge archive of targets that have been searched for radial velocity planets and use those archival observations to constrain the S indices as a function of time for these stars. And so that is our goal. Our goal is to measure calcium-2 H and K emission for about 250 stars every year or 2 for as long as we can until the wheels fall off. We will measure spectroscopic temperatures and metallicities of the stars using these high-resolution spectra. We are publishing the S indices that we measure in real time. So if you have science that you're doing on a planet hosting star and you want to know what its S index was in the last year, probably the only place you can find that information, if it's a northern target and it's bright enough, would be on our website. And so we're publishing all of this in real time as we collect it. And we are in the process of collecting observations in the archives from Mount Wilson, from HARPS, and from Keck to extend the time baseline as far backwards as possible so that we can really build up enough duration in addition to the so far only 1 year of observations that we've taken at APO to look for activity cycles and measure their duration. And so here's a brief by the numbers slide. We've had 23 half nights in the last year, with which we have observed nearly 200 stars. Our average uncertainty on the S index is about 4%, which we're very proud of because we know quantitatively what our uncertainties are, which is something that has not really been done very often in this part of the literature. And this is a kind of an ideal gap filling program because we can take bright time on the shell. And so we are proud to say that we are on average 71% moon illuminated, which is something that other people would kind of shriek in terror at, but we're proud of. And so we've covered a large number of the stars that we originally wrote down as potentially interesting stars, though there are many more in reserve that we could decide to observe in the coming year or two, should we decide to. If you look at the fraction that we've actually observed compared to the unobserved sample, you'll see that we are biased towards the later spectral types, which is partly because the later spectral types have more chromospheric activity on average. And so we have something to measure on those stars, whereas for a typical F star, there would be very little chromospheric activity. And so we're biasing ourselves towards the later spectral types. A talk on nearby bright stars would be incomplete without a reference to Gaia in this age. And so here is a color magnitude diagram constructed with Gaia colors and parallaxes, where the color of each point is denoting the S index that we've measured with APO. And you can see some interesting trends here. One is that the later spectral types, the stars to the right, tend to be more active on average. And the stars that are slightly evolved tend to be less active. And all of this has to do with the wonderful radiative transfer that occurs in stellar atmospheres. And I would point you to someone who's more of an expert on explaining why that actually happens this way, like Suzanne. And then I would like to show you one more plot of the S index versus color. This time I'm comparing to the sun, which is shown with the golden circle at about 0.65 and S index of about 0.18. The S index of the sun is kind of representative of a cluster of stars that sit near S indices of 0.2 between spectral types of like F5 and like K4. And inactive stars tend to fall in that range. Inactive stars of those spectral types tend to fall with S indices of about that quantity. But then more active stars can have S indices that are quite a bit higher. As you can see, a bunch of the TESS objects of interest, the TOIs that are labeled at the top of this plot, are stars that have spectral types similar to the sun's, but have S indices that are much, much higher. And that is likely because of their youth. And then you can see that as you go out to the later spectral types, the least active stars have a higher baseline. And so that's my my guidelines here. And I'm going to finish up in the next 30 seconds, Eric, before you get increasingly distracted. So there are a variety of measurements that we've taken that we're quite proud of that extend the legacy of Olin Wilson's survey that started in the 60s and continued into the 90s. And so here you can see this beautiful activity cycle that a star had that was started in the late 60s. And you can see the OWLS measurement on the right, which is near the maximum of the observed previous measurements for this star. And so we're really excited to continue to observe this star and see what it does. The same is true for several more stars. And I just want to give a quick shout out to one target that we've paid particular attention to. 55 Cancri is a planet hosting star that hosts a super Earth. And I published a paper this year that shows that its phase curve is difficult to explain without some kind of extra source of flux. Stellar magnetic activity may be to blame. And so 55 Cancri is one of the targets in our OWLS catalog. And you can see that we were able to pin down in the early 2021. The activity cycle is probably somewhere near its maximum when we started observing it, when you combine the observations that we have with the existing Keck high-res observations. So we're going to try to collect as many legacy observations as we can and as many future-looking observations from APO as we can, so that we can say something about whether or not the observations in the previous slide were taking near activity maximum or minimum. And I'll just close by saying our real-time S indices are available for you online if you want to take a look. And I'm happy to chat about the shell or stellar activity or anything on Slack for the rest of the conference. And thanks for your time.
All right. All right, thank you, Brett. I should have mentioned there are 3 ways to ask a question. You can raise your hand, and I already see hands raised. You can leave a message in the Zoom chat or leave a message in the Slack. But Don, I see your hand raised.
Thank you. So what do you have for information about stellar rotation periods, say TESS or other previous observations, or projected rotation rates V sin I from your spectra or others?
Thanks for your question, Don. The rotation rates of many of the more active stars are quite obvious in the TESS photometry, and most of our targets have TESS photometry. There are a subsample of stars that are a bit faint for TESS, but they are also coincidentally a bit faint for the Echelle. And so we tend to have rotation periods for the more active stars, which are skewed towards the later spectral types. And so I guess what I would say is that if you wanted to know the rotation period of an average F star, you would be hard pressed to find it from a TESS light curve or from a Kepler K2 light curve, because they tend to be pretty inactive. But if the stars have enough spots to generate rotational modulation, we often see them in the TESS photometry.
Okay, and I'll have to cut it off there, but remember, you can ask your question in the Zoom chat or in the Slack for the session if you have more questions for Brett. Okay, at this point, I'll